All right, so part two of this video really is, though I discussed it in class on Monday, it's really it's new material, and so we'll put it up as the Wednesday video. And the topic here is electronic shielding, charge shielding, and this is a super important way to look at the problem. And so what we're thinking about here is still helium and the various states of helium. But the reason that the topic is what's going on when we put the second electron into helium. So I've drawn here a 1s orbital on a radial coordinate. Looks like e to the minus rho. Rho is about half an angstrom in this case because it's a half a Bohr radius, excuse me, because the characteristic distance is the Bohr radius divided by the nuclear charge, and the charge is +2. So the first electron comes in. Think about it in terms of adding 2 electrons. And let's think about the first and the second electron. And the brown curve is basically what the second electron is going to try to do. That would be Juan. And my job is to motivate that. So let's think about this here. If we have helium plus, if we've got Clarissa and a +2 charged helium nucleus, Clarissa in a 1s orbital, 1s1 configuration is going to have an energy of -4 Rydbergs compared with completely ionized He2+ and electrons all over the place, far, far away. So Clarissa's there and happy and at -4 Rydbergs. And now Juan comes wandering into the scene. What's Juan see? So at a large distance, so there's 1, or E-, at a large distance, that He+ thing looks to Juan like a +1 charge. That's what it is. Looks like a hydrogen nucleus. If Juan's really clever, Juan will notice that his reduced mass is ever so slightly different from an electron and a proton, but Juan's not that smart. It's not that big a deal, it's not that much energy. Basically, Juan sees a hydrogen-like system because the charge, one of the 2 charges on the nucleus, is shielded by Clarissa. The point here is that the total charge that matters is just the total charge in a spherical shell closer to the point at the center of the charge than me. So when Juan is far away, all Juan sees is this +1 charge. So that means Juan is coming into this shielded system, and Juan basically thinks, geez, I'm coming into a hydrogen. I'm going to make a hydrogen-like system. And as long as Juan isn't heading dead toward the nucleus as well, Juan's probably got a little angular momentum. So just for the moment, let's put Juan into a 2p orbital. Now Juan sort of thinks that he wants to go into a 1s orbital, so we'll deal with that in a second. But basically, Juan's going to settle into an orbital that is at n = 2. Well, now what Juan really thinks he's doing is settling into a 1s orbital, and so Juan thinks that he has an energy of -1 Rydberg, a single electron next to a +1 charge. And if you take Clarissa's -4 Rydbergs, lucky Clarissa, and Juan's -1 Rydberg, I mean, after all, it is 110,000 wave numbers, so you really can't go complaining. You put those together and you get -5 Rydbergs. That's a lot of negative energy. If you will recall, when we were making our hand-wavy arguments about the energy of helium in the ground state, we said it might be about -6 Rydbergs based on geometric considerations. Here's kind of an upper limit, or a lower limit on the binding energy, an upper limit being the least stable energy. We get -5 Rydbergs if we figure that Juan kind of settles into it, rather than a 1s type orbital, into a higher occupancy, because Juan is fooled into thinking that the nucleus only has a +1 charge. We get -5, so we've kind of bounded the problem. And actually bounding problems and coming up with negative and positive limits and things is a really big deal in all kinds of applied math, but that's wandering a little bit off topic. So basically the idea is that as long as the nucleus, as long as the charge is shielded, then the second electron won't really notice that extra charge in there and will be less tightly bound. Now, the next thing that Juan can do is say, well, geez, I really wanted to make an s orbital. So if I want to make an s orbital, then it gets a little more interesting, because the reason I chose the 2p orbital at first was that the 2p is rather strictly excluded from getting too close to the nucleus. So it's conceivable that in the 2p, 1s1, 2p1 configuration, which is incidentally a triplet p2, and we'll learn about that over the next very short while, then Juan may never realize kind of what a raw deal he got. But if Juan gets into a 2s, Juan has a very high probability of getting very close to the nucleus. And when Juan gets very close to the nucleus, Juan realizes he's been gypped. Basically, the nucleus does have a +2 charge, not a +1 charge, because as soon as Juan gets closer to the nucleus than Clarissa, he discovers the full nuclear charge. And more than that, he exerts his +1, his -1 charge, and Clarissa is suddenly feeling kind of left out, like the nuclear charge just went from +2 to +1. And that all conspires. In the end, Juan and Clarissa kind of establish a little bit of a rapport. Well, it's more like the U.S. and the USSR in the Cold War. They establish a détente and settle into about -5.6 Rydbergs is their overall energy. But and they both settle into a 1s type orbital, as they more or less have to do. But the key concept here is this business of nuclear shielding, and the fact that the probability of being close to the nucleus is an incredibly important part of the overall problem. And now let's look at that when we think about what goes on and we're going to use the 3 s, p, and d orbitals as an illustration. So let's imagine Juan coming in and initially settling into an n=3 type orbital. So the deal is that in n=3, the 3s orbital is going to look roughly like this. Remember, the maximum probability in the 3s orbital is still to be at r=0. The place that if you have no angular momentum, you can get into r=0, and your maximum probability will be to be found in any given point in space at the point that is at r=0. But it's such a rare point that when we turn that into a probability distribution, r squared times the radial wave function squared, we get this sort of 3-lobed distribution, with the 2 0 points, 0 crossings being where the minima between the 3 maxima are. And the maximum radial probability distribution for the 3s electron is way the heck out there at that terminal maximum on the far right-hand side of the curve. Now if we go to the 3p, we add some angular momentum. So now with some angular momentum, there's no way, no how we can get into r=0. So it's like Tweedledum and Tweedledee in the Alice in Wonderland movie, right? No way, no how. It is not going to happen. So not going to get in there. And there's 0 probability, even in the wave function, of being at r=0. It's just not going to happen. So we turn this into a probability distribution, and we've got 2 humps instead of 3 humps. There's a secondary maximum and a primary maximum, again, out at large distance. And actually, if I'd drawn it properly, the 3p, as shown here, is the maximum probability, is, if anything, somewhat closer in than the 3s. But what it lacks is that really close in secondary maximum. There's the 3s up there. And then we go to the 3d. That's got a lot of orbital angular momentum, and it's got most of the energy in orbital angular momentum. So it is a strictly excluded, very hard exclusion around the low radius, because it just has to spin too darn fast to have the overall amount of energy, and it doesn't do that to have that angular momentum. And so the 3d has 0 radial nodes, 2 angular nodes, and it looks like this. And again, the probability distribution looks something like that. So the 3d is found nowhere close at all to the nucleus. It never gets close to it at all. And these secondary maxima are critical. They're totally, absolutely critical to the way that orbital occupancy plays out. Because remember, for the single electron case, there's no energy difference at all between the 3s, 3p, and 3d. N equals 3, and so we're going to look like minus z squared times the Rydberg constant for hydrogen times 1 over n squared, or 1 over 9 for n equals 3. And it doesn't say anything about SPDF. It doesn't care about what L is. It can only be SP or D, 0, 1, or 2 for n equals 3. But it doesn't care. It's just a limitation where I'm storing my energy. But when I have multiple electrons, just as we were talking about as we filled up the helium, then these secondary maxima are absolutely critical, because the 3s case has got these maxima closer to the nucleus, especially in the 3s, the one very, very close to the nucleus. That electron is going to discover, if it's in a multiple electron atom, that the electrons that are in lower energy, in other words, more tightly bound states, are hiding some of that nuclear charge from it. And it's going to be ripped about that, but it is going to wind up with overall lower energy, because it will spend some time very close to the nucleus, basking in that large positive nuclear charge. On the other hand, the 3p has only the single secondary maximum. We kind of pair that up with the 3s's primary maximum in a way, I suppose. But basically the 3p electron does get closer than some other things, so it gets some benefit, but it doesn't have that really close tertiary maximum there. And so it's going to be higher in energy. And the 3d finally is bereft. It has no idea that that final maximum it only has the single maximum at high angular distance, because the high angular momentum you can think of almost as a circular orbit. It's got as much of the energy as possible in that rotational aspect, and so it never gets anywhere near the nucleus. It never discovers any significant amount of that extra nuclear charge that is hidden from it by the shielding. And that is why the 3s, the 3p, and the 3d orbitals, once we have multiple electrons, are separated in energy, and by a lot. So the 3s electron is a lot lower in energy. The 3p is quite a bit lower, and the 3d is really doesn't get any extra benefit at all. And if you add to that the fact that the separation between the principal quantum number energy levels goes like 1 over n squared, meaning n equals 1 to n equals 2 is a huge step. N equals 2 to n equals 3 is a big step. 3 to 4 is not so much. That's why things start to get mixed up, and we develop a more subtle rule for the ordering of the total energy states when we start to populate atoms with lots and lots of electrons. But that's where it comes from.